Are there any questions? Did you all follow that? Okay. Okay. You're two goods, good X and good Y. Good X is the number of donuts, good Y is cups of coffee. So let's graph the constraints on here. You have your income constraint. Your income constraint is X plus Y is less than or equal to 50. And that will just look like this. Straight line with a vertical intercept of 50 and a slope of -1. Horizontal intercept of 50. So this is the income constraint. Oh, let's see. Do I have a, I don't have any other colors here today. Okay, that's all right. The calorie constraint would just be this one. The calorie constraint would be 200x plus 50y is less than or equal to 4,000. So if you graph this, just resolve this equation for y. And you could see at most how many cups of coffee could Ian get. What would be the most cups of coffee Ian could possibly get? 80. Okay. So that'll be the vertical intercept up here. Say 80 was right here. And at most, how many donuts could Ian consume consistent with his calorie constraint? 20. Okay. So this has a slope of -4. Comes down like this. This would be 20. And where do these two intersect? At x equals 10 and y equals 40. That's what we solved for earlier. So our feasible region, Josh, you're looking with a puzzled look. No, you don't. You don't. I'm just graphing it for now, Ian. So for graphical purpose, this is our wrong guess that we started off with. But you're right. Our feasible region is this area right here. Because we had to satisfy both constraints. We have to be on or below both. So it's this kinked frontier right here. Okay, that's our feasible region. We want to reach the highest indifference curve. And the highest indifference curve we solve for x and y. And what do we get for x? We got x star is 40 over 3. Got y star that satisfies the Kuhn-Tucker conditions is 80 over 3. And 40 over 3 would be what? What is this, 13 to the third? And 80 over 3 is twice as much, so this would be 26 2/3. That's where the highest indifference curve touches. And that would be along this segment right here. Notice, say right here. This would be our optimal point, where y was 26 2/3. Now we are assuming that Ian can consume fractional units. So they'll sell Ian a fractional cup of coffee, 2/3 a cup, for 2/3 the price of a full cup. And the same thing with donuts. And that means our highest indifference curve just touches right here. And if you substitute those values in, you get a utility value, the optimal utility. Utility is just x squared y. So if you substitute in 13 1/3 squared, 26 2/3, you get the optimal utility, which is, calculated it to be 4,740.74 joules, approximately. To the nearest second decimal place. Okay, and that's the highest indifference curve he could reach. So that would be his maximum utility. And notice, Ian, that this point is actually below the budget line. So this reflects the fact that at this point right here, Ian is not consuming all his income. But he is consuming, he is consuming 4,000 calories. So his calorie constraint is exactly binding, but not his income. Okay, so, and if you find the utility for this point right here, at the kink point, the utility for x equals 10, y equals 40, this would be 100 times 40 be 4,000, which is less. Okay. All right. Oh, by the way, so we have lambda 1. What was, if you calculate lambda 2 star, go back to what I had on the board, that expression for lambda 2 star. And what was the value for lambda 2 star? Let's see. What was our equation for lambda 2? It was, it was x squared over 50. So if you actually calculate this, you get about 3.56. It's positive, so that's good. If it were negative, that would indicate a problem. But it is positive. So what would be an interpretation of lambda 2 star here? 3.56.
There was a relaxation in his dietary restrictions from his doctor.
Yes.
We would see a 3.56 little increase in his utility.
Exactly right.
But you might have been getting that in the second part of the question, that if he consumes more and more donuts, this actually might decrease his health. So it might not be in his interest.
That's a limitation of the problem. The problem doesn't really explain what happens if you exceed the calories that your doctor recommends. Now, ideally, that would be that would affect your utility in a more realistic model. And maybe you could get away with consuming this sort of diet for a short period of time, but maybe it would shorten your lifespan.
That's why I found much trouble when you got
Okay.
this problem.
Okay. Well, your choices are very limited. They're just donuts and coffee. Those are the only two goods.
This is why I don't go to the doctor.
Yes. Okay. So a more realistic model would incorporate these features in a multi-period model where your health depends on your consumption. And if you violate the doctor's orders, that might catch up with you in the long run. Okay. All right. Okay. By the way, I drew these indifference curves as if they were convex. How could we verify that Ian's indifference curves really are convex? Okay. There's different ways you could do it. The easiest way to do it would just look at the indifference curves and show that each indifference curve is strictly convex. So I could rewrite this utility function this way. Y is equal to U times x to the minus 2. And then we're holding, along an indifference curve, we're holding utility constant, so you just treat u as if it were constant. So what is dy dx? Holding u constant. Right. Notice every one of the indifference curves has a negative slope. The slope of the indifference curve is always a negative. Okay. And then what's the second derivative? Yes, this would probably be the easiest way to do it. If the second derivative would be 6u times x to the minus 4. And that is what? Always positive. So that means for any given value of u, say u equals 100, the indifference curve is going to look like this. It is going to be nice and convex. It always has a negative slope. This is, say, for u equals 100. It always has a negative slope. dy dx is always negative. But as x gets bigger, the slope becomes less negative. The second derivative is always positive. And for bigger values of u, the only thing that will change is the indifference curve map. The indifference curve, the level, will be higher. But it will have the same shape. It always has a negative slope. Second derivative is always positive. So they always look like this. So certainly Ian's indifference curve map has convex indifference curves. Okay. That's what helps guarantee that that solution you reach is an optimal solution. See, I just drew it as if they were convex, but now we know that that's the case. So if I redraw this, looks like this. And you want to reach the highest indifference curve, but since they're all convex, you can't reach a higher one without violating the constraints. Now, if these indifference curves were concave, then you would have ended up with a corner solution, most likely. But since they're convex, this point right here, where you have this tangency right there, that gives you the Ian the maximum utility. Okay.
Is it possible to have a indifference curve on like a linear indifference curve?
Yes.
On a linear fuzzy constraint?
Yes, you could.
What would happen in this situation?
Well, suppose, notice this segment right here had a slope of -4, didn't it? Because 200 calories per donut, only 50 calories per coffee. So the slope of this calorie segment here, here's the calorie constraint, here's the income constraint, was -4. Suppose, Ian or Jacob, suppose your utility function is just this. 4y plus, oh no, I want to say, is it? No, I got to say y plus 4x. So then your indifference curve would be y equals u minus 4x. And what is dy dx here? -4. Your indifference curves now are straight lines with a slope of -4. So the highest one would lie right on top of this calorie constraint. Okay. If you consume anywhere along this border right here, you'd get the same utility. Because your indifference curves would just be straight lines that look like that instead of the curved ones. So in this case, anywhere along this segment right here would give you the maximum utility. Okay. In other words, in this case, it would be a peculiar case, but 4 coffees would be equivalent to 1 donut. So they would be perfect substitutes for each other. Okay. Well, I don't know. I don't think so. Let's look at that. Let me redraw the constraints here. Here's what our constraint looks like here. It starts at 80. And then, wait, okay. And then they cross right here. That's our income constraint. That's our calorie constraint. So our constraint is this area. Our feasible region is this area right here. Okay. This was our 80. This was our 50. This down here is supposed to be 20. Doesn't look like it's very accurate. And this would be 50 over here. Okay. But if they were concave, the indifference curves were concave, then depending on the curvature, you're either going to end up here or here, I think, for the highest. Well, let's see. I think suppose it looks like this. Okay, now maybe you're right. Suppose it looks like this. Zach, I think I take it back. In this rare case, you might end up at the kink point, but you might end up over here or over here, depending on the strength of the curvature. Yeah, you could.
Happen if you had perfect complement?
Yes, if you had perfect complements, it would depend on the ratio. So you could end up at this kink point here. But if they look like this, you might end up over here. So you could end up on this segment, or at the kink point. But that case, I think you have a good point here. Depending on the curvature, you could reach the highest one by consuming at that kink point.
I was also
Yeah.
curious
Yeah.
if we'd work with anything where we have, since we have 2 budget constraints,
Right.
theoretically we could end up with 2 optimal bundles, right? Or in this scenario, it looks like there could even be 3.
Yes, with a concave, not with a convex. So.
With convex, could you end
No.
up with 2?
No, not if our feasible region has this type of shape. Okay. Interesting. Good point. Well, this leads in to the discussion in the book on page 324 to 327. And this is getting at exactly at the point you asked earlier, Zach. How can we be sure, if you satisfy those Kuhn-Tucker conditions, that that gives you a maximum profit? And it turns out there are 2 theorems you can rely on to answer that question. The first, I'm going to call the Kuhn-Tucker sufficiency theorem. KT for Kuhn-Tucker. The Kuhn-Tucker sufficiency theorem, which is discussed in the textbook on page 424 and 425, imagines that you have a problem like this. And we're going to discuss it in the context of a maximization problem. Suppose you want to maximize profit. Profit is a function of x here. Now, x could be a vector. Could be x1, x2, xn. And all I'm saying is will follow. Okay, so think of x as being a vector, a 1 by n vector. Then you want to maximize that subject to these constraints. G superscript I. Okay, it's a book use an I or a J there. Sometimes I have trouble telling them, but it uses an I. G sub I of x is less than or equal to R sub I, where I goes from 1 to m. So you might have m constraints. Okay. And you're going to have, let's call it x sub j is greater than or equal to 0. Those will be your non-negativity constraints. And suppose j goes from 1 to n. Here we're going to assume n is greater than m. All right. So that is the problem. You satisfy the Kuhn-Tucker conditions. Okay, to satisfy the Kuhn-Tucker conditions. Suppose the objective function f of x is differentiable and concave. Okay. Suppose furthermore, that's part A in the book. Suppose furthermore each constraint function is differentiable and convex. Actually, it says we're assuming our function is differentiable and concave in the non-negative orthont. That just means that each of the x's is greater than or equal to 0. Okay. If you just had two variables, x1 and x2, the non-negative orthont would be this. It would be this area right here. In other words, x1 and x2 are both positive. So in this orthont up here, they're both greater than or equal to 0. Okay. So we're assuming each of the x's is greater than or equal to 0. Okay. So we're just dealing with a non-negative orthont. So in this region here, let's suppose our objective function is concave. And each of these constraints is convex. And then you satisfy the Kuhn-Tucker conditions, then that will guarantee that you have a global maximum. Okay. All right. So if your objective function is concave and each of your constraints is convex, you satisfy the Kuhn-Tucker conditions. This sufficiency theorem guarantees that you'll have a global maximum there. Okay. Now, the trouble with this Kuhn-Tucker